Hello, so I'm going to continue with the third part of transcendental functions here, okay? And now I'm going to talk about inverse functions. So what is an inverse function? If f is a function of x, okay, whatever, and there's also g, or we can put it like this, f and a minus. That means that's the inverse of this, okay? What does that mean? If this function right here turns x into y, what does that mean? Well, let's say if you plug in a 3 here, okay, so you plugged in the 3, and what you got back is a y of 2, right? In here, if you plug into the x of this function of 2, you're gonna get a y of 3. That's what it means, okay? You can say that this function turns a 3 into a 2, and this one turns a 2 into a 3. But saying it this way, it's not, doesn't really make too much sense because there's an ambiguity there. If this one turns a 3 into a 2, what is this? When I say that this one turns a 2 into a 3, what does that mean? That it turns a y into an x, or that it turns an x into a y? So it's all of these functions are going to turn x's into y's, okay? Except that when you plug in the value 3, you're going to get a 2 here. And when you plug in the value of 2 here in x, not in y, you're going to get a value 3. That's what it means. Okay, so I'm going to show you an example here. 2x cubed plus 1. And the inverse of x, okay, it's going to be... say here it's cube root of x plus 1 divided by 2. Okay, so there's something wrong. I knew there was something wrong. It's minus 2, it's minus 1 in here. So it's 2x cubed minus 1, okay? This one is gonna be x plus 1 divided by 2, and the cube root of all this, the cube root of x plus 1 divided by 2. So if you plug this value in here, you're going to get an x, right? Because there's this property too, that if you take the f of what? Of f of x, this is going to be an x. And the same thing goes the other way. So if you have the inverse here of f of x, you're going to get an x, okay? Why? Because in this case, you got to work from the inside out. So first you worry about this and then worry about that. So the f inverse of x, this is going to transform this x into a certain y value, okay? Now when you get this y value and you plug it in to this function here, this is the part that's confusing. It's going to turn back into an x, and you go like, okay, so the outer function is going to turn a y into an x? No, it's still, both of them are going to turn x's into y's, okay? But it's just that if the x in here in this function is a, and it transforms it into a b, you get this b value, and you put it in the x of the inverse function, and it's going to transform it into an a. But they're both transforming x's into y's. They're not transforming y's into x's, okay? So this is going to be the same thing, this value of y here. So it's going to be plugged in here, right? Well, because this is going to transform it into a y. So this thing here becomes f of y, which is going to be x. So you see, that's weird, because it seems that it's transforming a y into an x. No, it's not. Okay, actually what you have is a big X in here with the value of Y, and a big Y in here with the value of X. So, but they're both transforming X's into Y's. Okay, so I'm going to leave it like that, fine. So let's try that. I'm going to plug this one here in here, okay? So you got the cubic root, right? Of, what is this? See, you're going to plug this into here, so it's going to be 2x cubed minus 1 plus 1 divided by 2. So this minus 1 and the plus 1 go away. This 2, you can divide it by this 2, and you have a cube root of x cubed, which is x. So you see, when you plug this into this, you got an x. What I did was just this thing here, guys, is this. I did this. All right, and now I'm going to do the opposite. You have 2. I'm going to plug this stuff in here into this x. So it'll be the cube root, okay, of x cubed. So these things are going to cancel out. I'm going to do it anyway, just very slowly, so you guys can see it. So I put this in here, into this value x, which is cubed, and you have a minus 1, okay? So since the whole thing is cubed and it's at a cubic root, you can cancel this with this stuff in here. And now you have this equals 2 times x plus 1 divided by 2 minus 1. You cancel this one with this one, you're left with x plus 1 minus 1 equals x. So again, I did this, okay? All right. I'm going to show you something here. The inverse function, okay? So here you got, let's call it, yeah, this is the function, and this is its inverse, okay? So you can see that they're symmetric to the line y is equal to x, right? That's it right here. Now let's try to see this a little bit better. You see, whenever you have a point in here close to 1, it's not 1, but you can say that it's like 3/4 maybe, all right, 0.75, let's just pretend that it is. It's transforming the whole thing into 0. So for the f of x, f of 0.75 equals 0. Okay, so you have a y, I have an x and a y, and you got a 0.75 in here, you get a 0. But guess what? When you put on the other side an x equals 0, what you get is a y of 0.75. So the inverse function, which is in this case g, okay, is transforming a 0. You plug in 0 for x, you're going to get a 0.75 for y. This point right here is this one here, that one, okay? But again, they're all transforming x's into y's. They're not transforming y's into x's. All right. Let's keep going. Yeah, there's something else too. Whenever you have a function, for it to have an inverse, okay, it has to pass the horizontal line test, because if you have something like this, it's not a function because it fails the vertical line test, okay? It's hitting here and it's hitting here. For a graph to be considered a function, the vertical line, any vertical line here can only hit one thing, okay? Like that. Otherwise, it's not a function. It's a relation. Now, I want to show you guys why, because some people don't get this in their high school math or whatever. So let's just say that you got sales here. So you have sales, right? And here you have the month. So you got a graph like this, right? And you can see that it passes the vertical line test because this is a function. Why? Because for every month, well, for this month right here, let's just say that this is a month, and this is another month, and this is another month, and this is another month. You can see that you only have one sales, right? At the end of, for example, January, you got to have sales. At the end of February, you got to have sales. But let's just say that instead of a graph like this, I started with something like that. That means that in the month of February, look at this, you had something in sales here, and then you have something else, and then you had something else. Let's just say that you had $10,000 in sales in January, and in February you had $20,000 and $30,000 and $40,000. So which is it? I mean, how much did you sell totally in February? Oh, I sold the three at the same time. I had a total sales of $20,000 in February, and in the same February I had a total sale of $30,000 and a total sale of $40,000. How? You can only have one. So that's why when it fails the vertical line test, it's not a function, it's a relation. Okay? Now, for a function to have an inverse, it has to pass the horizontal line test. Okay? So this one passes the horizontal line test too. Doesn't matter where you put a horizontal line, it's just going to cross the graph once. Why is that? Because let's go again here, okay, and let's make a graph like this. So it fails the horizontal line test. It hits in here and in here. Okay, why does this function that makes this graph doesn't have an inverse? Because when you put the function, for example, you put f of a, it's going to transform it into b, okay? But when you put the f of b, it's got to transform it into a. F inverse of b, it has to be equal to a, okay? Okay, well, let's just say that you got an a here, and you have, well, let's see here first. First, I'm going to do this. I'm going to pass a horizontal line, and then this a is actually going to be kind of in here. Yeah, this is the reway, not this one. This is the reway. Okay, and the other one is here. It's a C. Okay, so look at that. How can it have an inverse? And this is a point B for y. Okay, this is a point B for y, and this is also B for y because it's at the same height. So when you do the f of a, you get a b. But when you do the f inverse of b, you can get an a or you can get a c. So which one is it? A or a c? So which one is it? Is it A or is it C? So it doesn't have an inverse. Okay, for it to have an inverse, x has to have a one-to-one correspondence to y, and y has to have a one-to-one correspondence to x. So from the value of y, you have to get back to x. That doesn't mean that you're transforming y's into x's. That just means that you're transforming x's into y's. So if you have a x equals 2, you're going to have a y equals 3. And if you have an x equals 3, you have to have a y equals 2. But that's not the case in here. If you have an inverse function of f, which is f inverse, okay, this is not f to the minus 1, this is just f inverse. It's just a notation of b. You can either go to A or to C. So how do you know where you're going to go? You don't. So that's why you got to have a one-to-one relationship. Okay. So here are a few examples. Already showed you. Fine. Yeah. Now. F of x equals cube root of 2x minus 3. Cube root, the square root of 2x minus 3. Find the inverse. Okay. Which one is it? Well, all you got to do is to isolate this x, because you gotta undo what it does so you can get an x from this. So what would you do? Okay, I would get another x. This x in here is not this one, guys. Okay, this is another x. This is the x of the inverse. I would get this x and I would square it. That's going to leave me 2x minus 3. And then I'm going to add a 3. And then I'm going to divide it by 2. All right, that is going to give me, so that's the inverse. But is there, well, yeah, I was able to do this, but is there some easier way to do that? Yes, you do it like this. Y equals the square root of 2x minus 3. So you want to isolate this x. So you square everything, right? And x is just going to be equal to y squared plus 3 divided by 2. After the x is isolated, you switch the x and a y, okay? So now switch the x and y's, and you're going to have y equals x squared plus 3 divided by 2. And there you go. This is what you're going to plug in here, okay? So that's the inverse. Gonna get this, and we just plug it in here. There you go. There's something else too that I don't know if I've shown you this already, that the function and its inverse are symmetrical to the y equals x line, okay? So if it's coming here, it's coming here. If it does this, whatever, then it's gonna do this in here. Oh man, this is so dark that it's so bright that even I can see. If it does something like this, then it has to do something like this. Okay, this is there you go, and you can see that they pass the vertical line test except at this point. Okay, but they pass everywhere the vertical line test. It just crosses once, and they also pass the horizontal line test. The horizontal line test passes the graph only once. Okay, see that? There you go. Now, you can see something else, the derivative of an inverse function. Okay, let's just say that the derivative exists and it's not 0, right? So you have f, a function f, okay, and its derivative. The derivative is going to be equal to 1 divided by the derivative of the inverse. So I'm going to put a minus here to show that this is the inverse, and I'm going to do this to show it's a derivative. I'm going to put this prime in here of what? Of f of x, right? So yeah, and here you're going to have x too. So this is kind of complicated, but you can see that it's just going to be the reciprocal, okay? It's just that, let's just say that, you got here f, and you have an f prime, f inverse, okay? When you put, here you're going to have x and y, like that. Man, what a mess. Okay, like this. So if you put, for example, a 0 here and it comes up with a 4, if you put a 4 here, you're going to come up with a 0, okay? So the derivative over here is going to be the derivative at this point is going to be reciprocal to the derivative at this point. Okay, that's what this means, and I'm going to show you a graph because it makes it a whole lot easier. The graph in here, increase the size. I don't know if it's going to be easy enough to see. So anyway, you see this function right here, I'm going to have to, the contrast so low that even I can see it. This function right here, okay, f of x, and here's the inverse, f inverse. I'm just going to call it f inverse. So you can see that this one, okay, is coming over here, f of x, and it transforms a 2 into a 3, okay? So you have a 2 here, and you have a 3 here, that's this point. That's fine. And you can see that the slope in here is going to be, this m is slope, okay, it's going to be 4. Well, you see, what's going to be the inverse? The inverse is going to get a 3 as an x and it's going to transform it into a 2. So you got it over here, okay? Now, because they're symmetric on the y equals x axis, the slope has to be reciprocal, because let's just say the slope in here is coming like this, just at this point, okay? Okay, so you got that slope in there. That, I'm gonna put it a little bit up so you can see it, okay? So that's the slope, and you see it goes 1 up, just the slope right here at this point, it goes 1 up and 4 units to the right, okay? But because it's symmetric around about the y equals x line, this one here has to be the opposite. It has to go 4 up and just 1 to the right. So that's why the slope is 4. And that's what this notation over here means, okay? So you have the derivative of x is going to be the reciprocal of the derivative of f inverse. Okay, this looks like a -1. It's going to be the derivative of f inverse at that point that it was the y of the previous one. Okay, so this one, f of x, not the f prime of x, the f of x transformed some x into a value y. Now you get this value from y, you plug it into the inverse, and you're going to get the previous value of the x of the previous version, of the previous function. It's really complicated, but that's why this image right here makes it so much simpler, okay? This image right here makes it a little bit easier to visualize what's happening, because look at the slope in here. The slope in here is going to go kind of like that. Yeah, kind of like that. Okay, so while this one here is going just 1 up and 4 to the right, this one here is going 4 up and 1 to the right. Okay, this one transforms the f inverse transforms a 3 into a 2, and the f transforms a 2 into a 3. So yeah, that's what it means. Now we're going to do some exercises. You have an f here. Well, this is the f, okay, so the prime, the first derivative is going to be 3x squared divided by 4 plus 1. Okay, so it's asking for what is the value of f inverse of x when x equals 3. Okay, so it's asking for the g of 3. Which one is it going to be? So you see here, what you have here, guys, is like it's asking for g of 3. Okay, it's asking for the g of 3. Now remember, the g of 3 is going to transform this into a value of y. Okay, hold on. Oh, actually, yeah. So this 3 here is going to transform it into a value of y. And when you put this value of y, whatever it is, when you put this value of y in here into this function, the whole thing is going to be equal to 3. So what you have to do is to equate this equation to 3. So you have x cubed divided by 4. Okay, I want to put the whole thing, so plus 4x minus 4 equals 3. So everything is equal to 12. Okay, putting that 4 in here is going to be equal to 16. So I'm going to already is 16 in here. So you have x squared plus 4 equal to 16. Okay. Well, actually, And this is not the way I'm gonna have to solve this. I have to do it another way, like x cubed plus 4x minus 16 equals 0. So let's try to do this by inspection. If you put a 1, it's not going to work. If you put a 2, yeah, if you put a 2, it's going to work. So one of the things in here that's going to make this 0 is a 2, right? 2 is going to be 8 plus 4 times 2, 8. 8 plus 8, 16 minus 16, 0. Okay. So we know that the f of 2 equals 3. Right, let's try to do that. 8 divided by 4, 2, plus 2, 4, minus 1, 3. Okay, and we know, therefore, that the g of 3 is going to be 2. Okay, this is the way we solve this. All right, and now, what else is value? What is the value of the inverse when x equals 3? Okay, so it's asking for the derivative. It's asking for the derivative of 3. What is it going to be? Well, remember, the derivative of 3 of x, whatever it is, so say in this case it's 3, according to that theorem, it's going to be 1 divided by the derivative of the inverse, okay, of g of 3. Okay, now what is g of 3? G of 3 is going to be 2. So this equals 1 over the derivative of the function at 2. We have the derivative of the function here. So at 2, it's going to be 4. So 3 plus 1, 4. So this is going to be 1/4. That's it. The derivative at 2, okay, f of 2 is going to be 4. So since this one has to be the reciprocal, it's 1/4. And that's it. Okay. Here's another interesting one. Okay, the function is equal ln of x. Now let's try to find the inverse. What is it going to be? Well, what does this mean? Okay, this, you can say that this is equal y equals ln of x, and this is a natural logarithm function. This is a natural logarithm notation, so this means e to the y equals x. So there you go. We already isolated the x. So all you got to do now is to switch the x and y. So x e to the x equals y. You get this thing and you plug it in there. So see, ln of x and e to the x are inverse of each other. Inverse of the reverse of each other. And here's the graph. There, see? They're symmetrical to the one, they're symmetrical about the y equals x line. Okay. So a function in its inverse are symmetrical about the y equals x line. So you have a 7 here. This is just an exercise. 7 equals e to the x plus 1. And it's asking to solve that. Well, what you can do is to take the ln of both sides. So you have the ln of 7 equals the ln of e to the x plus 1. Okay, now there's a property, guys, that says, for example, if you have the log or the whatever, you have the log on the base b, okay, and here you got a base b elevated to a, for example, this whole thing equals a. right? This whole thing equals this. So here, because it's a natural logarithm, the base here is e, okay? So this base and this base are equal, everything equals the exponent. So let's do that. This base here is e, this one is also e, everything here equals x plus 1, the exponent right here. So x plus 1 equals the ln of 7. Therefore, x equals ln of 7 minus 1, which approximates to 0.946. Another one is the ln of 2x minus 3 equals 5. Okay, that means that e to the fifth equals 2x minus 3, and you can say that x equals e to the fifth plus 3 divided by 2. It's very simple. Do that in a calculator. This approximates to 75.707. And I think that'll be it for now, guys. Yeah, that'll be it for now.